All right, we're going to take a look at number 2 from our 11.5 notes on probability plus permutations and combinations. In number 2, it says Florida has a lottery game called Lotto. It is set up where a participant chooses 6 different numbers from 1 to 53. If the 6 numbers chosen match 6 numbers that are drawn randomly in any order, so this is a pretty big piece here, any order, the contestant wins $10 million. And we want to know is what is the probability of choosing a set of winning numbers? Now, one of the keys here is that it's in any order. So that means we're looking at combinations rather than permutations. The order doesn't matter. Because previously, on this previous problem, we were looking at permutations because it did matter who spoke first and who spoke last. The other piece is that we also had a couple sets of limitations, but didn't lock us completely, where we still had some fluctuation in some of the other days, which led to us having, on part B of question 1, having 18 possible situations where we could end up with that, meeting those requirements. Here on number 2, there's only one set that we can have. We either have all of those numbers or we don't have all of those numbers. So we actually only have one combination that works. So I'm going to write one working combination. Now that makes this a little bit easier in some aspects, but it also tells us that what we're drawing 6 numbers from 53 different numbers. So that means we're working with that NCR function. So NCR, which if we replace with the values that we want, it's going to be, we're choosing from 53, and we're choosing 6 of them. So if we set that up in the formula, it's going to be 53 factorial, and that's going to be over 53 minus 6 factorial, which will also then be multiplied by 6 factorial. So doing that 53 minus 6, it's going to end up giving us 47 factorial down here. We still have the 6 factorial. And the reason I haven't written the numerator is because I know I want to cancel out this 47 factorial. So I'm going to go ahead and write this 47 factorial over here, because I'm going to want to cancel it out. Extend that a little bit. Now, what I need to do with that top number is I have 53 factorial, but I'm pulling the 47 out of it, so that means I need to count down from 53 and I kind of ran out of space here. But we have 53 times 52 times 51 times 50 times 49 times 48 and then times 47 factorial. Now, we have a 47 factorial in the numerator and a 47 factorial in the denominator. Those are going to cancel out, which was really the whole purpose of that. Which leaves behind, in the numerator, 53 times 52 times 51 times 50 times 49 times 48. And then the denominator, we still have 6 factorial, which we could expand out to be 6 times 5 times 4 times 3 times 2 times 1. You could also use the factorial function on your calculator for that. And what we'll find is that if we multiply the numerator, it comes out to be 1.65 times 10 to the 10th power, which really means that we moved that decimal place 10 places to the right, over 720. Which when we divide that out, it's going to end up coming out to be 22,957,480 different possible combinations of numbers. Now, this is our total, so we still need to do the probability. So the probability for this is going to be, we have one working combination, and we have 22,957,480 possible combinations, so it's going to be 1 over 22,957,480, which really is not a good chance. Which, if you want that as a percentage or a decimal, let's just do decimal, it's actually 0.000000044, which is a 0.000044% chance. Not a great chance of winning. If you have any questions, again, like I said in the last video, I'll be gone until Friday, but you can shoot me a loop mail, and I'll hopefully be able to get back to you pretty quickly.